Hi everyone. This morning we're going to look at independent events. Okay, it's another topic in probability. And again, we start off with a silly example that needs some volunteering from the audience, except I don't have an audience. So we're going to go and pretend again that I have 25 students. And we're going to call 15 females and 10 males. Okay, we've been pretty well sticking to that. I am going to tell you that 5 people in the class are left-handed, meaning that 20 are right-handed. 3 people in the class went to St. Kevin's, and everybody else went to elementary school someplace else. Okay, someplace other than St. Kevin's. And I'm going to tell you that I found one person who is left-handed and went to St. Kevin's. Who knows? Maybe it's Graham Staples. Maybe it's Reese Biskey. Not sure. So if you could take a moment and write that down. 25 kids. Let me just move it, scooch it a bit. 25 kids, 15 males, and 15 females and 10 males. 5 left-handed kids, 20 right-handed kids, 3 St. Kevin's kids, 22 kids that went to someplace other than St. Kevin's, and 1 person that's left-handed and went to St. Kevin's. Again, maybe it's Graham, maybe it's Reese. Okay, so that's our information. Let's start looking at our questions. What is the probability of selecting a student in our class that's left-handed? Again, standard question. Write down what you're looking for. Bottom number is 25. That's our NS. And out of those 25 people, we said that there were 5 that were left-handed. What is the probability of taking a look at our class and finding somebody that went to St. Kevin's? Again, blank fraction, 25 on the bottom. And St. Kevin's people, we're pretending that we found 3. Okay. What is the probability of selecting a student from our class who is left-handed and who went to St. Kevin's? Again, 25 people in our class. This is the overlap. This is the person who, let me just write that down. Overlap, intersection. This is the person who's left-handed and went to St. Kevin's. And we're going to pretend that there's 1. What is the probability of selecting a student from our class that's left-handed or went to St. Kevin's? Now, we are quite familiar with the OR, having 2 techniques, the visual technique and the formula technique. Okay, so there's absolutely nothing new here. Visual technique, I'm going to have a left-handed circle and a St. Kevin's circle. I have 1 person who is left-handed and went to St. Kevin's. I supposedly had 5 people who were left-handed, 1's being accounted for. I supposedly had 3 people who went to St. Kevin's, 1's being accounted for. And if I add those numbers, 4, 6, 7, that means that there's 18 people that are non-left and non-St. Kevin's. These are my right-handed kids. So the probability of being left-handed or St. Kevin's when we're doing it from a visual technique is we just add the numbers in the circle. 4, 5, 7 out of 25. Now, if I look at it from a formula, we're going to have the probability of left or St. Kevin's equals the probability of being a left-handed person, 5 out of 25, plus the probability of being a St. Kevin's person, 3 out of 25, minus the probability of being left and St. Kevin's. And again, we were joking and teasing around. Maybe that's Graham, maybe that's Reese, right? 5 plus 3 is 8, minus 1, 725. So via the visual, via the formula, same answers, absolutely nothing new. A silly example that we can all kind of relate to. Okay, let's keep going. What is the probability of selecting a student from our class that's left-handed? We already answered that. What is the probability of rolling a 4 on a die? Well, 6 sides to a die. A 4 would be one of the 6 sides. These two events are considered independent of each other. Now, when I say independent, it means they have absolutely nothing to do with each other. I mean, left-handed and St. Kevin's also don't have anything to do with each other, but we did find an overlap. I usually do every single semester. I'll find one kid at least that went to St. Kevin's and is left-handed. But these two things, they are so remotely different that you're never going to find an overlap because they're completely so obscure. Okay, let's keep going. And let's see what the theory says here. Independent events are events that have absolutely no effect on each other. No effect whatsoever. Going to St. Kevin's and rolling a die, no effect whatsoever. Mutually exclusive is not the same thing. Okay. Why not? Let's find out. Mutually exclusive events are events that can't happen at the same time. So having a green eye and a brown eye, it's unlikely to happen at the same time. Independent events are events that are so completely obscure, have nothing to do with each other, they have no effect on each other. So it's not that they can't happen at the same time, it's like that they don't even have anything to do with each other. So let's again keep on looking at some silly examples before we get into sort of the hardcore. What is the probability of flipping a head? So you have a coin, and you know that it's 50% chance of flipping a head. Okay. What is the probability of flipping a head if you just flipped a head? These are what we call independent events. The fact that I took a coin and I flipped a head, and then the fact that I flip another coin and I flip a head, they have nothing to do with each other. Okay? The first flip has no effect on the second flip. They are independent of each other. That's what I want you to understand. There's no effect. The first event has no effect on the other. Okay, let's keep going. What is the probability of selecting a student from our class that is left-handed and rolling a 4 on the die? Well, if there's no effect, the rolling the 4 has no effect, what do we do? There's absolutely no overlap. They're completely obscure. They're not related to each other. what do? When they're independent, when they are independent, we can multiply the two separate probabilities. So probability of being left-handed, we said was 1 over 5, 5 over 25. And probability of rolling a 4 on a die was 1 over 6, 1 over 30. So hold on, let's take a look. The word and indicates that we are looking for an intersection. We know that. How do we determine the intersection of two sets that are completely independent? We multiply them. We multiply them. Okay, let's keep going. What is the probability of selecting a student from your class that's left-handed or rolling a 4? Well, with this particular one, because there is no visual, oops, sorry, I spelled visual wrong. We must use the formula. So your hand is forced with these type of questions to use the formula. So the formula will say probability of being left-handed, 1 over 5. Probability of rolling a 4, 1 over 6. Minus the probability of being left-handed and rolling a 4. We just calculated that right up here. 1 over 30. That's going to take a little bit of work. Let's get some common denominator going here. 6 over 30, 5 over 30, minus 1 over 30, 11 minus 1, 10 over 30, or 1/3. So probability of being a left hand, we had 5 people, 5 out of 25, which is 1/5. Probability of rolling a 4, 1 over 6. Probability of being left and rolling a 4, 1 over 30. Common denominator, 1/3. So let's make sure we're clear. Mutually exclusive events can't happen at the same time. Independent events are events that have no effect on each other. They're completely obscure. They have nothing to do with each other whatsoever. Okay. I think we need to look at some real life examples. A game consists of rolling a die and drawing a card from the deck. Find the probability that you roll a 6 and then an ace is drawn. These two events are independent. So probability of rolling a 6 and picking an ace. Geez, I don't know why I wrote rolling like that. Hold on. That wasn't too smart. There we go. So rolling a 6 would be 1 over 6. Selecting an ace would be 4 out of 52. Independent events, rolling a die and picking a card, they have nothing to do with each other. So 4 out of 312, 1 over 78. So I hope what you're discovering is that the and has two different scenarios. The and can be the overlap or the intersection, but the and can also be multiplication if events are independent. The or also has two scenarios. The OR can be done visually. If you've got a dice chart, if you've got a Venn diagram, if you've got some sort of chart rather. And the OR can be done via formula. So things are all coming together with different types of questions. If you have two events that there's no hope in hell of ever even drawing a picture or a chart like these two, you've got to multiply them. Okay, that's what this is saying in simple English. Now, I want you to put a bunch of stars, because this is the classic type of question that you would see, okay, on a test with regards to the OR. Okay, let's take a look at it. Chris figures that he's got a 60% chance of passing math, and Meg has an 80% chance. Now, Chris and Meg, they are in two different classes. They're not friends. There's nothing. They're just two independent people. So the probability of Chris passing and the probability of Meg passing are two completely different numbers. And two completely different people, two completely independent events of each other. Well, 60% for Chris and 80% for Meg. There's no way that we can draw a picture. 48%. What's the probability that Chris passes and Meg doesn't? So Meg fails. Now, hold on. If it's a 60% chance of Chris passing, that means it's a 40% chance of him failing. If it's an 80% chance of Meg passing, then it's a 20% chance of her failing. So careful, let me go up and highlight. 60 pass, 40 fail, 80 pass, 20 fail. So Chris passing, 60%, Meg failing, 20%. What's the probability that both fail? So Chris fails and Meg fails. Again, 40% chance of Chris failing, 20% chance of Meg failing, 8%. Okay. What's the probability that at least one of them passes? You got a couple different ways of looking at this. Okay. At least one of them passing means the probability of Chris passing, or the probability of Meg passing, or the probability of Chris and Meg passing, because at least one passing means one of them passes or both of them passes. Okay, so hold on here for a second. If Chris passes, that's a 60% chance, and that would mean Meg fails, which is a 20. Chris passes, but Meg fails. Meg passes, 80%, but Chris fails, 40%. And both of them passing, 60% and 80%. So hold on and let's look at this for a second. At least one of them passes. The first scenario is Chris passes, but Meg fails. Second scenario is Meg passes, but Chris fails. So that's one of them passing. Second scenario or final scenario is both of them passing. So 12%, 32%, and 48%. 44, 92% that at least one of them passes. Now, I could also look at this from reverse psych. At least one passes means one passes or two passes. Opposite to the question is that nobody passes. So that's going to be the probability of Meg failing and Chris failing. Well, Meg failing is 20%. Chris failing is 40%. 20 times 40, 8%. 92% pass rate. Okay, this last question is a very, very standard question. You'll see it pop up. Please make sure that you practice it. Okay, it's kind of like your go-to question on an assignment or a test for independent. Thank you so much. Take care.